All right, good morning, everybody. Hope you're all doing well. Hope you're hanging in there today. Welcome to week number 5. I know it's kind of like you blink and we're already here. Things are going a lot faster than anticipated. That being said, let's jump in. So today we're going to wrap up talking about Earth's history. I'm allergic to history, so I'm kind of looking forward to that. And we're going to start getting into more of the science behind climate change. So up to this point, we've talked about the history of climate science. We've talked about how we know what we know, why we know what we know. Today, we're going to wrap up talking about what we know from the past. And then we're going to begin talking about heat, energy, temperature, and the greenhouse effect. So that's sort of segueing into what we're going to be talking about this week. That being said, here is today's warm-up question. Let me post it both in chat and put it up on the screen. And here we go. So today's warm-up question deals with something that I'm sure that we've all experienced at some point, at least those of us who have cars or have ridden in a car in the afternoon, and that is that the inside of your car, even if it's not that hot outside, can get really, really warm. Why do you think that is? And so to answer that question, as is tradition in this class, you can answer it using the Google form linked in chat. And then the other thing I'm actually doing is I'm also linking it on Canvas. So if you go to Canvas, click on announcements, I just posted the link there as well. All right. So take a few moments, chew on this, and then we'll talk about it. I'll paste it a few more times in chat as well. There we go. All right, so for those of you who just joined us, we are doing today's warm-up question. It's on the screen, and then I just put the link again in chat. Gonna keep an eye on how many people, whoops, let me move that real quick. Sorry about that. Keeping an eye on how many people have submitted it yet so I can kind of have a sense as to when people are done. As always with these warm-up questions, I'm not looking for perfection. I just want to know your thoughts. So any guess is better than no guess. All right, let's take about another minute to begin wrapping up this question, and then I'll go over what people have said, and then we'll jump in. All right. Looks like a few more people still need to make submissions, but I am going to switch over. And let's see what the general consensus, the general idea coming out of the answers here happens to be. Okay. So in a summer sunny day, it doesn't take long for a car to reach upwards to 127, 150 degrees. When there's more humidity in the air, the car takes in more heat than it usually does. Okay, so humidity might be a factor. Sunlight passes through the windows, in the interior of the car, absorbs and radiates that back out as heat. Okay. So this idea that sunlight is getting through the windows of the car, being absorbed by the interior of the car, and then a lot of that energy that is absorbed by the car is then radiated back out. Okay. Let's see here. The temperature of that inside of the car matches the temperature outside of the car. Because the car is such an enclosed space with no way for air to get through. So there's definitely that too. There's that lack of ventilation that goes on in there. The sun is constantly hitting the car, and since the car is like a big metal box, it heats up quite a bit. Also, people don't usually leave their windows down. I always try to crack my windows. Let's see here. I also know that some people don't do that for security reasons, for fear of somebody breaking in. But I do that because, yeah, it gets really hot. Let's see here. I think the inside of a car can get hot during a sunny afternoon because the air that's trapped in the car is being heated by the sun. Okay. The whole car is being heated by the sun. A car gets hot on a sunny afternoon due to so much exposure from the sun. So a lot of people are talking about sunlight. Let's see here. The sun is hitting them. It absorbs all of the sun's energy and traps heat inside of it. So there's something about your car that lets sunlight in, but whatever's in there gets trapped. Okay. That's definitely what's happening, by the way. Let's see here. And that combined with the idea that the windows aren't cracked, the the car is very much isolated. I believe how compact your car is plays a significant role. Okay. From my understanding, the afternoons are the hottest hour of the day, and it's sunny on top of that. So, conduction. We're going to talk about conduction next time. Most metals are really good at conducting heat. So that's something that can play a role. The heat cannot escape from the inside. So once again, sunlight is passing through the windows. Heat can't escape from the inside. The heat stays in the car. Air gets trapped in. See here. The air inside the car is not moving, so stale air can definitely cause this. Gets a lot of contact with the sun's rays, lack of ventilation. For my car, the interior is mostly black, so on a hot afternoon, it absorbs that heat and makes it hot. So something to do with the color of the interior actually plays a huge role. Next week, we're going to talk about this property called albedo. And I actually have a cool demonstration. Hopefully it'll be clearer than it is outside today to actually show you how albedo works. And so let's see here. The sunlight gets trapped inside the car. Okay. So putting all of this together, it really looks like you all did a very comprehensive, very awesome job at answering this question. So that being said, let me give you the big answer, the big how this works. All right, so first off, let me get a pen set up. Okay, so here's your car. Very poorly drawn. That's why I didn't go to art school. I studied science instead. My spelling is the other reason why. So here's your car. And up here is good old Mr. Sun. I know, where else in college do you hear somebody call it Mr. Sun? Well, the sun is emitting a lot of light, right? That's why it brightens things up during the daytime. That's why it keeps things nice and glowing, and gives us all that light outside. And the way it does this is via something called shortwave radiation. Shortwave radiation. Now, the bulk of shortwave radiation is visible light. And you want to be able to see visible light. You want to be able to see that light because you want to be able to see the car in front of you, or the hazard on the side of the road, or the pedestrian in San Francisco who doesn't obey traffic laws. I mean, all of those different things, you want to be able to see them. So the windows of your car are transparent to that kind of light. Well, in addition to that visible light, there's also a bunch of other stuff called ultraviolet radiation and near-infrared radiation that can actually heat things up very quickly. And the windows on your car are very transparent to that. So then your car absorbs, the interior of your car actually absorbs this radiation. So what happens to the temperature of the interior of your car when it absorbs radiation, when it absorbs heat? Well, it heats up, right? When something absorbs heat, it gets hotter. But what happens is as temperature goes up, the interior of your car actually gives off radiation as well. It gives off a much different type of radiation called long wave radiation. And basically what long wave radiation is, it's mostly far infrared radiation. It's the same type of radiation our Earth gives off, and it's the same type of radiation you and me give off. Yes, we actually give off radiation. Well, those windows that were nice and transparent to shortwave radiation aren't so nice and transparent to longwave radiation. Instead, they block it. They keep it from escaping. They keep it trapped inside your car. Well, this long-wave radiation is a form of heat. So the heat stays inside your car. So that's sort of the long-winded scientific explanation of why your car gets so hot. Now, why would I even bother talking about this? Well, in the next few class sessions, we're going to be talking a lot about the greenhouse effect. And this is actually the way that the greenhouse effect works. In fact, that's where it gets its name, the greenhouse effect. It comes from the idea that a greenhouse, which is basically a big glass box, is very, very good at letting heat in, but not so good at letting it out. That allows the temperature inside the box to warm, and then that keeps everything inside the box nice and warm. Well, in our atmosphere, there are all these little gases that do the exact same thing. They let sunlight in, but they don't let heat out. Or at least they don't let the kind of heat that Earth gives off out. So this just segues us into a lot of what we're going to be talking about in the next few class sessions. Now, before I jump into that, I did want to talk for a few minutes just about a few housekeeping things. So my grader Tyler graded all the homework this weekend. He did one thing that I wasn't happy about, and that was he didn't leave any comments on your work. So I apologize for that. What I actually did, though, to help with that is I posted an answer key that shows you exactly how the assignment was graded, exactly how I told him to grade it. So what I'd like you to do is between now and next class, look over that answer key. And if there's anything that you're still uncertain about, unclear about, we can talk about it next time, because I definitely want to make sure that you know what you got right, what you got wrong. And I will make sure that in the future, either Tyler or myself are leaving comments. That way we're not, that way you're knowing how you're doing on these assignments and what you got wrong. And so I didn't anticipate he wasn't going to put any comments down. So that's good to know for the future. So I do apologize for that. And I'm going to get that squared away. And what I can also do is go over the homework a little bit in depth next time as well. All right. So that being said, let's jump into what we're talking about today. So what we're going to start with is we're going to start by wrapping up what we were talking about last time. So last time we were talking a little bit about history. If you're like me, you might be allergic to history, but we got to get through it, because so much of why climate change, or so much of the question of is what's happening now concerning can't be answered unless we look into the past. Now, what I talked about last time, I talked about things such as the formation of the Earth, heterogeneous versus homogeneous accretion. We also covered the formation of cyanobacteria and how they kind of created the seesawing effect of Earth's temperature. First, temperatures declined, and we have what was called a snowball Earth. Then temperatures skyrocketed, and we had what was called a hothouse Earth. And then I briefly talked about these 3 major ice ages that have happened in the past 1 billion years. And one of the things that I didn't really mention yet is that we are still currently in this ice age. We're actually currently in an ice age right now. Yeah, we are technically currently in an ice age right now. Now, that being said, The ice age that we're in right now is very different than what you see in the movie Ice Age, where poor little Scrat's trying to get the acorn. We're not in that kind of ice age, but we are actually in a pretty interesting period, and we are having major impacts on that. The last thing I talked about last time was some of the cataclysmic events that have happened historically. So I wrapped up last time by talking about what happened to the poor old dinosaurs. So roughly 66 million years ago, an asteroid collided on the Yucatan Peninsula of Mexico. That's that little area in the southern portion of the Gulf of Mexico. And it is believed that that is what triggered the extinction of the dinosaurs, and actually the extinction of many different things. Well, these cataclysmic events can cause very sudden, very drastic climate shifts. Now, asteroid impacts aren't the only thing that we've dealt with before. Another thing that we've dealt with, actually much more often in terms of geologic time, is supervolcanic eruptions. So when I talked about recent climate history last week, I talked about the eruption of Mount Pinatubo. And when Mount Pinatubo erupted, it actually caused global average temperatures to drop by about 0.5 degrees Celsius in a very short period of time. Well, that's nothing compared to supervolcanic eruptions. So think about this. Mount Pinatubo was what we call a VEI 6 eruption. So VEI stands for Volcanic Explosivity Index, and it's a scale that is out of 8. Oops, actually, let me write out of 8. So it registered a 6 out of 8 on the Volcanic Explosivity Index. What that actually means, though, they actually based this index on how much stuff the volcano shoots out. Mount Pinatubo shot out around 10 cubic kilometers of ash. So think about a cube, 10 kilometers wide, 10 kilometers deep, 10 kilometers tall. For those of you Americans, that's 6.1 miles deep, 6.1 miles wide, 6.1 miles tall. That's a lot of ash. Well, supervolcanic eruptions, actually let me write, this was Pinatubo. Supervolcanic eruptions are actually an 8 on the VEI scale. And the bare minimum that a supervolcanic eruption will let out is 1,000 cubic kilometers of ash. So think about a cube 1,000 kilometers wide, 1,000 kilometers deep, 1,000 kilometers tall. That is enough to cover the entire west coast of the United States by ash that is 1,000 kilometers tall. Well, actually, no, that's not fair. Be more like 500 kilometers tall. That's still a lot of ash, and that would still destroy us. Now, the good news is that most of this ash doesn't cover one area. Instead, it spreads around. The bad news is that a component of this ash is this molecule called sulfur dioxide. And sulfur dioxide is very, very, very reflective of sunlight. Very reflective of sunlight. As a result, a lot of sunlight that would be heading towards the surface of the earth gets bounced back out and the Earth becomes a lot cooler. So these volcanic eruptions, just like asteroid impacts, are responsible for major and sudden climate change. Now it's okay because supervolcanoes aren't very common. I think the most recent number I heard was there were 25, I think, around the entire world. And every one of them has a different frequency of eruptions. The one that we know, the one that we're most famous for here, is the Yellowstone supervolcano. So if you've ever been to Yellowstone National Park before, and you've seen Old Faithful erupt, or you've seen many of the other geysers, or have actually gone down to some of the prismatic pools and so on, the hot springs, that is all fueled by an underground supervolcano. And that volcano erupts with a frequency of about once every 600 to 800,000 years. By the way, the last time it erupted was 640,000 years ago. What does that mean? Let's take a look here and see. Somebody just asked me, where are all the supervolcanoes erupted? So there's actually two here in America. There's Yellowstone, and then there's another one over here in what's called the Long Valley. Was there climate change with the Mount Vesuvius eruption in Pompeii? Yes, but Mount Vesuvius was very similar in intensity to Mount Pinatubo. So there was climate change, but it was very brief. So it was just like Mount Pinatubo. There was roughly a year of cooling, and then things, once all the dust settled, things got back to normal. Some of these other supervolcanoes, a lot of them are located in Indonesia. Indonesia is a very, very volcanically active region. There's a few other that are located underwater. I actually don't have a map of all of the supervolcanoes, though. Now I'm going to look for one. Usually when I talk about supervolcanoes, I mainly talk about Yellowstone. So the Yellowstone volcano, the Yellowstone caldera, the super erupting volcano, erupted 2.1 million years ago, 1.3 million years ago, and 640,000 years ago. What does that tell us? If you look at the frequency of these eruptions, what does this kind of indicate?
It's on course to erupt like the next, I don't know, whenever, pretty much.
We're due. Yeah. We're actually due for an eruption. Now, the good news is that when I say we're due for an eruption, I'm talking about in geologic terms, on the geologic time scale. What that means, when I say we're due, it could be tomorrow, it could be 100,000 years from now. And so the chance of it going off any given day, very, very, very low. Not only that, but these things don't just suddenly happen. There are a lot of warning signs. And nothing is suggesting that right now. Nothing is suggesting that it's going to erupt anytime soon. But just keep that in the back of your head. I mean, it is 2020 after all. So, as I mentioned, Yellowstone isn't the only supervolcano. The last big super eruption that happened in world history was about 75,000 years ago. During that time, there was what was called a genetic bottleneck. Basically, the genetic diversity of humans suddenly plunged. And the reason why was because of this super eruption. It is believed that at one point, the human population was down to about 1,000 breeding couples. And the total population was as little as 3,000 people. think about where you live. If you live in the Bay Area, chances are there are 3,000 people within a mile of you. If we were on campus, I'd say, oh, there's 10 times that many people here on campus right now. Unfortunately, we're not on campus. But that being said, 3,000 people, that is a very small number, even for that time period. That is a very small number. That is frighteningly little. So it almost wiped us out. Now, our technology, our ability to produce shelter and so on, are things that would keep it from getting as bad now, but it could still get pretty bad. So these are just a few things that can actually affect climate, both in the short term and in the long term. Usually most of these cataclysmic events, meteor impacts, super volcanic eruptions, these, believe it or not, tend to be very short-term events. Meaning they happen, they kick up a bunch of dust. That dust may cover things for 5 years, 10 years, 15 years, 20 years. In geologic time, that's nothing. And then things kind of go back to the way they were. We'll actually talk about another big eruption that happened much more recently later in class. So let's talk a little bit more about this ice age that we're stuck in right now. So the ice age that we're currently in right now is what's called the Pleistocene Epoch. Kind of a weird name, but that's the name that it was given by many, many scientists who have worked on developing an understanding of ice ages. So about 10 million years after the big asteroid impact that killed the dinosaurs, about 10 million years after that, a more marked cooling trend began. So prior to that, Earth was a very, very warm place. It was very warm, very lush, very humid. And then temperatures began to decline about 55 million years ago. In the past 2.5 million years, we've actually been in the ice age. The weird thing about this ice age, though, is that it hasn't been continuous. Rather, it's been this hodgepodge of different glaciation periods, different periods where glaciers on Earth were growing and spreading, and then periods where they were shrinking and pulling apart. These interglacial periods are warmer periods of retreating glaciers. So these are times where glaciers pretty much only were near the poles. During the more glacial periods, that wasn't the case. At a point, during some of these more recent glacial periods, we had ice as far south as the US-Canada border. And that was all around the world. So most of jolly old England was covered in ice. Much of Western Europe, a place that we have widely populated, was covered in ice. I won't even go into interior Russia, Siberia, Eastern Europe, other areas, because those already get cold. They were way colder during that period. The most recent glacial period occurred roughly 22,000 years ago. It was the most recent glacial advance. During that time, polar regions were roughly 15 to 20 degrees Fahrenheit. That is approximately 6 to 11 degrees Celsius cooler than they are today. Actually, it's more like 8 to 11. Sorry, didn't use my toes properly. And tropical regions were 5 to 10 degrees cooler than they were today. During that time, because there was all of this ice, there was much less ocean, and as a result, sea levels were much lower than they are today. This exposed what was called the Bering Land Bridge, and it's actually believed that the exposure of that land bridge is what allowed people to move from Europe, Asia, and Africa across to North America. It's believed that's what allowed it to do. Or it's believed that that's what was or that's what happened during that time. That's that exposure of the Bering Land Bridge allowed humans to actually cross over into North and South America. Because before then, we were very, very, very separated. So there was a brief warm period about 14,000 years ago. And then in North America and Europe, not the entire world, just North America and Europe, there was another dip in temperatures called the Younger Dryas period. And that was the last cool period. Now, I know what some people would be thinking. Okay, Terrence, so it's clear that we kind of go through these interglacial periods and then these glacial periods and so on. What does that actually tell us about today? Well, the last time we pulled away from one of these glacial periods, one of these periods of major cold and glaciation, we were warming at a pretty set rate. The current rate of warming that we are in now is actually about 10 times as fast. So we are actually warming right now at a rate 10 times quicker than we did when we pulled out of the last ice age. That's pretty alarming. So we are warming up much faster. The other thing is right now we are not in a glacial period. We've been out of a glacial period for roughly the past 11,000 years. So we shouldn't be warming more and more and more. In fact, if you actually were to take all of the natural forces in effect, if you took human activity out, we should actually be cooling again. Earth's global temperature should be cooling, but that's not what we're seeing. So this right here, this is using ice core data as well as sediment sample data. The bulk of this comes from the Vostok ice core. This is actually a reconstruction of roughly the past 400,000 years. Here's what you're looking at. Up here, this is carbon dioxide concentrations in parts per million. We've talked about ppm already. Anybody remember where are we at now? Approximately what is our carbon dioxide concentration now? Approximately what is our carbon dioxide concentration now? What is our current carbon dioxide concentration?
Are we like in the 400 ppm?
Mm-hmm. Yeah. So we're around 400 parts per million. If you take a look at this scale here, so somebody messaged me 409. We vary every year between roughly 409, 410 to 415. It keeps going up every year. That being said, this scale ends at 300. If we were to actually look at where we're at today, we would be somewhere up here. Approximately. Let me make sure that I'm actually we'd probably even be a little bit higher. But I think you get the point. Carbon dioxide concentrations are higher now than they have been any time in the past 400,000 years. Here's the other scary thing though. Down here in this bottom panel, we actually see global average temperatures compared to today from compared to today, compared to the present. And if you notice, as many people have said, yeah, climate changes happen or they happen in a cycle. Is there a relationship between temperature and carbon dioxide evidenced in this? One person in chat said yes. So what do you notice about the shape of these two graphs? Somebody says seems like it shows as peaks in carbon dioxide. Okay, I'm lagging a little bit. I do apologize for that. So let's see here. I do apologize for that. Yeah, the internet in my house actually broke last night, and I haven't been able to get AT&T to come over to fix it. So I'm actually using my Wi-Fi on my phone right now. So I apologize if the quality isn't as good as it normally is. I really apologize for that. Thank you for letting me know. Hopefully they come this afternoon and this all gets fixed. So you notice, once again, the high points in temperature happen right around the same time as the high points in carbon dioxide. And then when CO2 was low, temperature was low. What I'm actually going to have you do for the second homework assignment, which is now up on Canvas, is actually investigate this graph a little bit more. Investigate when the peaks were, when the bottoms were. So this is the past 400,000 years. As I mentioned as well, we've been through the periods of, as you saw on that graph, we've been through these periods of warmer temperatures, followed by these advancing glaciers, followed by warmer temperatures, followed by these advancing glaciers. Well, this was basically how Earth looked 18,000 years ago during the last major ice period, during the last major glaciation period. If you notice, all of Canada was gone. All of it was covered in ice. Pretty much the entire Midwest of the United States was covered in ice. All of the Northeast of the United States, so this includes New York, which is right here, Boston, which is right here, DC was right on the edge, right here, all covered in ice. Parts of Northern California and Southern Oregon covered in ice. And then if you look over at Europe, all of jolly old England was covered in ice. as well as Ireland, Scotland, and Wales. The entire British Isles were covered in ice. All of Northern Europe was completely covered in ice. Iceland was indeed icy, as well as parts of Spain, France, Germany, Northern Italy, the Alps, as well as the peninsula. All of Russia was already cold, but now it was covered in ice. So this was how it looked 18,000. And this has basically been those last 18,000 years. We were in that period of cooler, ice-covered time. Then, roughly around 14,000 years ago, temperatures went up. Then they dipped again a little bit, mostly in North America and Europe during the Younger Dryas period. Then, roughly 10,000 years ago, we had a big jump in temperatures. And then we've kind of been hovering around just sort of this current norm for roughly the last 10,000 years. There was a little jump in temperatures around 4,000 years ago called the Holocene maximum. There was a little about Ice Age, but roughly last 150 years, we have seen a sharp jump in temperatures. We're already about to surpass the Holocene maximum, and we're just getting warmer and warmer and warmer. Here's, if we zoom in and just focus on the past 1,500 years, roughly the first 1,300 years of this graph were reconstruction based. So that included a lot of the proxies we talked about last time, ice core, sediment samples, and so on, tree rings, all of the things we can use to reconstruct past climate. And then this has pretty much been everything recorded on instruments. And what you actually see is, if I were to draw a trend line, there's a little bit of a dip, then a huge jump. Almost kind of looks like a slightly kinked hockey stick. And we oftentimes call this the hockey stick analogy, because temperatures have just jumped substantially in the past roughly 150 years. There was another little period of cooling that happened right around here called the Little Ice. That's the last like big historical climate thing that I need to talk about, the Little Ice Age. So the Little Ice Age occurred roughly from the 15th to the 19th century. So this is roughly 1400 to 1800 when the Little Ice Age occurred. Now, obviously, since the Little Ice Age, we have way better records now. The good news is that even without these records, we have much more detail of the past roughly 1,500 years of temperatures in general, because even though we didn't have the equipment to measure them, we were able to still say, hey, it was really hot during this time, or it was really cold during this time. So increases in human observation, and then now the development and improvements in instrumentation and so on have allowed us to create much more detailed records. Much more detailed records. So what we've had here in the Northern Hemisphere, temperatures have primarily been cooler than they currently are. If we actually go back to that graph, you can kind of see that. This black line represents the 1961 to 1990 average, so roughly those last few months, or sorry, months, oh my gosh, Tuesday morning brain, those last few decades of the 20th century. But we have jumped up significantly since then. There were a few exceptions. In the 11 to 14, talking the years 1000 to roughly 1300, much of Europe and parts of North America were a little bit warmer than they are today. In fact, it was so warm that Greenland was actually seen as a pretty attractive place for people to go. And the Vikings, which had been expanding during this time, settled in Greenland. Then the Little Ice Age came, the 15th to 19th centuries. That's when the Little Ice Age came. And those same Vikings that settled on Greenland died. Got too cold for them. What's interesting, though, and also a little disturbing, was that during the Little Ice Age, cooling was not worldwide. It was primarily in North America and Europe. Primarily in North America and Europe. The reason why that's disturbing is that there's a potential explanation that could have really major consequences for us today. When I say today, I mean like currently, like present, during like our current era. So this was a cooling event that occurred in Europe and North America from roughly 1400 to 1800. So that's the Little Ice Age. So let's talk about this Little Ice Age a little bit more in depth. So as I mentioned, cooling was not worldwide. Instead, it was mostly Europe and North America. Much of the rest of the world did not experience this. We don't have an exact answer as to what caused it, but there are a few prevailing hypotheses that actually have a lot of evidence now backing them up. One of them was a substantial increase in solar activity. So how many of you have ever heard of sunspots before? Sunspots? Anybody here hear of sunspots? They're kind of like little freckles on the sun. Well, what happens is when these occur, these actually occur during times where the sun is giving off more energy. When the sun is basically giving us a little bit more heat. Well, currently, sunspots cycle from periods of maximums to periods of minimum roughly every 11 years. Well, during almost right around the same time as the Little Ice Age, roughly around 1600, there was a period of time where there were almost no sunspots. Sunspot activity just completely went away. And we call that the Maunder minimum. One of the big holes that we can poke in this argument, though, is that if this was the cause of the Little Ice Age, this would have been a global cooling caused by fewer sunspots. But that's not what we got. Much of the world stayed nice and warm. It was only North America and Europe experienced cooling. So the other explanation, and the much more concerning explanation, the thermal hailing conveyor. How many of you, let me try something really quickly. How many of you have ever seen The Day After Tomorrow before? It's roughly a 15-year-old movie. How many of you have seen The Day After Tomorrow before? Oops. Participants, click on more. Okay, so one person saying no. haven't, let's see here if that kind of cleaned up my internet a little bit. Well, if you haven't seen it, you're not going to get a lot from it. It is a piece of fiction, and many meteorologists say it's a piece of something else as well. Well, in the movie, there was one piece of accurate science, and it had to do with this thing called the thermohaline conveyor. And basically what happened was, in the movie, the thermohaline conveyor shut down, and that caused giant land hurricanes with eyes in the middle of them, you know, like a hurricane does, that froze people on contact. It was definitely very, very, lots of like, no, this isn't realistic. But let's actually talk about the real science behind this and why this is concerning today. Here's that Maunder minimum I was talking about, just very briefly going through that. This absence of sunspots, whoops, I don't know why that's advancing on me. Okay, so this was an absence of sunspots that, as I mentioned, 1600, a little bit after 1600, from roughly 1645 to 1715. I was slightly off on the dates, but one of the things you'll learn in this class, dates aren't important except for Friday and Saturday night. Well, during this period, solar activity was definitely very, very minimum. We don't know what caused the Maunder minimum, but during this time we saw a pretty noticeable decrease in solar activity. And this is one of the potential explanations for the little ice age. The big hole to poke in it is the cooling would have been worldwide, but it wasn't. So here's the other explanation. The other explanation is the thermohaline conveyor. Now I know what you're thinking seeing this. You want to withdraw from the class now. I hope not. I promise it's not that bad. We're not going to focus on the whole thing here. But basically what this is this is a giant global ocean current that involves both surface parts and deep parts of the ocean. Now, there's a lot of different components to this, but really the most important component to this is the transition zone from surface ocean current to deep ocean current. And that happens to happen right here in the North Atlantic. In the day after tomorrow, they refer to it as the North Atlantic Current, which is actually a component of what the thermohaline conveyor is. Well, here's what happens. Up towards Europe. It actually makes its way up and along the US East Coast as a part of what's called the Gulf Stream. This warm water then makes it up to this area between technically between Greenland and England, right next to this little island called Iceland. And right here, it gives off a lot of its heat to most of Europe. So it gives off a lot of its heat towards Europe, making Europe nice and warm. Well, a very important component of this current, as I just mentioned, is its ability to give off its heat, but also its ability to then sink afterwards. Well, the ability for water to sink is dependent on two things: temperature and saltiness. When water is very cold and salty, it's really, really dense. Well, here, as the water gives off its heat, it becomes very cold and salty and sinks. It's that sinking that fuels this entire current. If that sinking didn't happen, this current would not happen. What's scary is that if the saltiness of this part of the current were to decrease, if it were to become less salty, the water wouldn't sink. So if it were to become less salty, if the salinity, that's this fancy term for how salty the water is, if the salinity of the water becomes lower, meaning that the water is less salty, it won't sink. So we would need something to dilute this water, to make it less salty. Any guesses as to something up here that could dilute this water? If you needed to dilute something, you would want to add fresh water to it. Well, what is a source of fresh water up there?
Ice.
Ice. Somebody else just messaged me that as well. Ice. Well, is there a big source of melting ice up here? Is there a big source of melting ice here? Whoops, I'll go back to that in a second. Yes. Yeah, believe it or not, there's a big source of melting ice, and it happens to be right here, Greenland. Why is Greenland icy and Iceland green? All about deception. Well, Greenland is very, very icy, but that ice is melting. And a lot of that melted ice is actually rushing right into that area where the salty water sinks. So right there, we get this sudden dilution. What that does is that prevents the water from sinking as fast. That slows this current down. Now, here's the scary thing. The scary thing is that if this were to happen, this area up here would start to experience record cold. Well, guess what's happened in the last 10 years? This area up here has actually begun to experience record cold. It's actually now colder up here. This is one of the areas, one of only the areas in the entire world that are actually cooling. Well, the scary thing is that if this trend continues, this could result in a complete shutdown of this conveyor. And that would greatly decrease the amount of heat transfer happening. And that would greatly decrease the amount of heat that Europe could receive. So if this trend were to continue, it is very possible that parts of Europe and North America could suddenly become much colder than they are today. And we believe this is potentially what happened during both the Younger Dryas period, that period where pretty much mostly North America and Europe got really cold, and then during the Little Ice Age, this period where North America and Europe got really cold. However, in those periods, the conveyor slowed down. What we're afraid of And yet, really apologize. Um, so basically, the idea here is that if this were to happen again, we could have political instability. Okay, somebody else is messaging me now. TNT screws up like right at the most inconvenient time. Anyone else having a really bad connection? No, it's not you, it's me. So it's not you, it's me. So I really apologize. Let me write that here in chat for people who can't hear that. Unable to fully hear me. Can people hear me now? Okay, people can hear me now. Okay. I'm really sorry about that, everybody. Definitely the internet connection issue is something that I need to look into. I'm going to be on the phone with AT&T later, chewing them out, threatening to switch to Xfinity. I'm sure it's no better there. These telecommunications companies have pretty bad, but anyway, the TLDR version of this is Europe could suddenly become much colder. And a lot of people aren't going to be able to live in parts of Europe anymore, and they're going to have to move. And that could be bad. Xfinity is actually much better. Good to know. So the last thing I want to talk about are a few recent things. So now we're kind of getting more into the more recent stuff that's happening. So I mentioned earlier, I talked about supervolcanoes, and then I've talked about Mount Pinatubo. There's one other major historical volcanic eruption. In 1815, on April 10th, 6 days before my birthday, Mount Tambora, a mountain in Indonesia, erupted. This was actually a VEI 7 eruption. So remember when I talked about that VEI scale of 1 to 8? Mount Tambora was a VEI 7 volcanic eruption. That means that it ejected over 100 cubic kilometers of ash. Well, what this did was this much ash getting into the atmosphere isn't going to wipe everything out like a super eruption like Yellowstone, but it's going to create more than just a little dip in temperatures like with Mount Pinatubo. This is kind of like the intermediate stage. It got so bad that there was actually a point in 1816 where there was snow and ice falling in July and August. Yes, our friends in Denver got a snowstorm last week, but it's very uncommon for America, for any of America, to experience a snowstorm in August or July. And yet that happened in 1816. Now that might sound cool. If you're like me, I love cool weather. But if you're not like me, like if you're a plant, plants don't like cool weather. They like warmer weather. They like more fertile temperatures. Lots of crop failures happened during 1816, and big global famines happened during 1816. Well, 1816 is now infamously known as the year without a summer. 1816, the year without a summer. So this was all caused by the eruption of Mount Tambora. Last thing I want to show you before we wrap up today is carbon dioxide concentrations in the past 10,000 years. This is a pretty telling graphic. If you notice, in roughly the past 10,000 years, carbon dioxide concentrations were relatively steady. A slight increase over the past roughly 6,000 years. But then, pretty much from 1850 on, carbon dioxide concentrations have just rocketed up. And some of the worst case scenarios now have carbon dioxide concentrations doubling by 2100. To me, this is the most telling graphic about climate change. This is pretty much like the smoking gun of climate change. Just the skyrocket in carbon dioxide concentrations. So what's so alarming about all of this? Like, why did I even talk about history when I've said I'm allergic to it? Even though I'm not really, but, well, the point here is that Earth has natural periods of warming and cooling. So why is this one so concerning? Why is the warming we're experiencing now so concerning? Well, it's not so much the fact that Earth is warming, it's how fast Earth is warming. It's the rate at which warming is occurring. Right now, we are warming at a rate about 10 times as fast as when we emerged from the previous glacial period. Temperatures have not been this warm, not only in the past 1,500 years, but actually roughly the past 4,000 years. We're already surpassing the Holocene maximum. Temperatures have only varied within 2 degrees in the past 10,000 years and 8 degrees since 1880. Since 1880, we have seen between 0.65 and 1.05 degrees of warming. So we have seen a lot of warming in a very short period of time. We don't see this kind of warming this quickly. That is what's scary about this. And when you look at how carbon dioxide concentrations have gone, and you actually look at the total reconstructed climate, what we are seeing now is unprecedented. Now, what's causing this? Well, carbon dioxide concentrations going up is a big thing. But why is that something that we even need to think about? Well, we'll talk about that next time. I apologize again for the laggy internet. I'm going to get it fixed between today and Thursday. If you have any questions, comments, concerns, I can stick around for a few minutes. Thank you all for bearing with me today. Have a great day. Stay safe, and I'll see you all soon. Bye.
Thank you. Bye.
Bye.
Thank you.
Bye. Thank you.
Thank you all for bearing with me today. I can hang around for a few minutes for anybody who is has any questions or needs any help. Yeah, there's still a few people in the room right now. If either of you have any questions, I can gladly answer them. Otherwise, I will see you next time. Alrighty.